For the differential equation, dy dx equals x, y is equal to 3 when x is equal to 2, estimate the value of y when x equals 3 using h is equal to 0.5. Now, it sometimes helps to set this out as a table. So I'm going to have x, y, dy dx, h, and then delta y. So for our first step, we'll start with the values we were given. X is 2, y is 3. Since dy dx is x, that means dy dx would be 2. H is the step length, which we're told is 0.5. And as we saw in the introduction, delta y is what you get when you multiply dy dx and h. So 2 times 0.5 is 1. If the step length is h, our next value of x is 2.5. Just add 0.5 onto 2. And then the y will be the current y, add the change in y, so 3 plus 1 is 4. Then dy dx, well in this case, since it's just equal to x, is 2.5. H stays at 0.5. 2.5 times 0.5 gives me 1.25. The next x is 3, which is where we want to get to. So our last step is just this next value of y, which is the current y, add the change in y, 5.25. Now while we're here, let's look at a couple of things. This is a very easy differential equation to solve. Dy dx is x. Integrate both sides with respect to x, and we get y is x squared on 2 plus a constant. We know that y is 3 when x is 2, so 3 is going to be 2 squared divided by 2 plus c, gives us c is equal to 1. So y is equal to x squared on 2 plus 1. And if we work out y of 3, that's going to give us 3 squared on 2 add 1. So that's 9 divided by 2, 4.5 add 1 is 5.5. So this will be the absolutely accurate answer. This is what we estimated using Euler. We could have been much more accurate than that if we'd used a smaller step length. We can also look at this using the calculator. So we want to be in this one, recursion. So we're going to press 8. And this is the one that we want, although we can click on the type and we can see different types, but the one that we do want was F2. That's the one we had open already. And what we want to do is the next A, these are our X values that we put in the A's, that is going to be AN, in this case, add 0.5. Let's enter that. And then, so that's going to step the x's along in 0.5s. For the b's, what we're going to do is we're going to have bn, which is going to be the current value of b, and then we need to add to that the step length, which is 0.5, multiplied by the differential, which in this case, with it just being dy dx equals x, is just going to be an. And then we can just go to the table here. Actually, we can't go to the table just yet. We have to go to set, sorry. Now, I've already set this one up with my a0, my first x being 2, and my y being 3. And so that one is okay, so I can just exit from that. So I can now just go to the table, and there we can see that the second value, when x is 3, the y is 5.25. But let's have a look at, we know that the true value is 5.5. Let's try and do that a bit more accurately. So if I just exit from there, let's maybe make, instead of 0.5, let's make that something like 0.01. And then in the next table, I'm going to also need to make the 0.5 there 0.01, because that has to be the step length in both cases. Now I definitely need to go to set here because I've only got table ending at 5, and we're going to need a lot more than that. Let's make the table go out to 100, and we'll execute on that. We've got the same start values, and so we can exit from that now and go to table, and you can see it's going up in much smaller increments now, and we can go down there, and we wanted what happens when x is 3, and so we're going to need to go a long way down the table, and that's why it's not even using the calculator often going to be asked to use very small step lengths, but we can see the value is getting close now, 2.98, 2.99, 3, 5.495, which is much closer. So the small step length really makes a difference.